In the summer of 1881, a farmer in rural Pennsylvania made a quiet modification to his land. He buried a 40-foot line of clay pipe 4 feet beneath his wheat field, routing the terminal end directly into the stone cellar of his farmhouse. For the next 6 decades, while his neighbors weathered the brutal midsummer heat of the Atlantic states, his home remained remarkably cool. When agricultural inspectors finally surveyed the property in 1947, they recorded an indoor temperature of 61 degrees Fahrenheit on an afternoon when the outdoor mercury surpassed 94 degrees. There was no electrical grid connection, no mechanical compressor, and no synthetic refrigerant. The climate control relied entirely on a subterranean pathway and a baseline principle of planetary physics. For over a century, traditional agrarian communities across North America have quietly replicated this mechanism. They refer to it simply as an earth tube. While modern climate control industries have spent decades focusing on complex, energy-intensive machinery, these communities have relied on the Earth itself as a massive, passive heat exchanger. The core physics are public, measurable, and entirely decentralized. The underlying science requires no specialized technology to understand. Anyone who has ever stepped into a subterranean cave during the height of July has experienced the mechanism firsthand. If you measure the soil matrix approximately 6 feet below the surface across most temperate climate zones, the temperature remains remarkably stable, holding steady between 52 and 57 degrees Fahrenheit year-round. The surface atmosphere can experience extreme heat waves, localized droughts, or sub-zero winters, but the sheer thermal mass of the Earth acts as a massive dampening filter. The top layers of soil insulate the deeper ground, creating a permanent thermal equilibrium that barely fluctuates more than 2 or 3 degrees across an entire calendar year. To leverage this equilibrium, you introduce an air pathway. By burying a continuous line of pipe horizontally between 4 and 8 feet underground, you create an environmental transition zone. The intake, ambient air, enters the external opening at whatever the current atmospheric temperature happens to be, whether it is 90 degrees, 100 degrees, or higher. The transition, as that air is drawn through the subterranean pipe, it continuously surrenders its thermal energy to the surrounding cool soil. The discharge, by the time the airflow travels a distance of 50 to 100 feet, it emerges into the living space as cool, balanced air, typically hovering in the low to mid-60s Fahrenheit. Because this setup relies on thermal conduction rather than mechanical refrigeration, it features no moving parts, no compressors to burn out, and no chemical refrigerants to replace. A properly configured underground pipe can remain fully operational for generations. While traditional builders optimize this approach through trial and error, modern academic research has confirmed the raw efficiency of the physics involved. In 2019, an engineering study published in the journal Energy and Buildings evaluated the precise performance of a 60-foot buried polymer pipe. The material cost of the underground infrastructure was negligible. Yet, the data revealed that the system yielded a cooling output equivalent to a standard 1,200-watt mechanical window unit, while drawing zero grid electricity for the thermal exchange itself. The only power requirement was a small inline fan pulling roughly 35 watts, the equivalent of a small light bulb, to maintain steady airflow. The study calculated the seasonal coefficient of performance, the standard engineering metric used to evaluate cooling efficiency. Standard central air conditioning operates at a COP around 4.0. A subterranean earth heat exchanger operates at 40.0 or higher. An earth tube can operate at an efficiency scale multiple times greater than a conventional high-end mechanical cooling system. This data is entirely public, yet it is rarely highlighted in mainstream architectural design. The reason is structural. A passive pipe buried once requires no recurring maintenance contracts, no seasonal component replacements, and no proprietary software updates. It does not fit into a consumer model designed around recurring revenue. Long before laboratory data verified these coefficients, off-grid communities kept the engineering alive by utilizing natural pressure differentials. In traditional architectural designs, these cooling tunnels operate without any electrical assistance by capitalizing on the stack effect. As warm air naturally rises and exits through the upper levels of a structure via open high-altitude windows or roof vents, it creates a subtle negative pressure zone on the lower levels. This internal vacuum pulls the dense, cool air upward through the subterranean pipe network automatically. The system regulates itself passively. It functions at noon, during peak thermal load, and continues operating seamlessly if the regional electrical grid fails entirely. In contemporary adaptations, builders sometimes add a low-voltage 12-volt DC fan powered by a single standalone solar panel to accelerate air exchange during periods of high ambient humidity, but the foundational logic remains strictly passive. Despite the simplicity of the physics, executing a subterranean air exchanger requires strict adherence to specific engineering rules. Public discussions on internet forums are frequently filled with accounts of systems that developed moisture or odor issues. Virtually every single one of these failures can be traced back to three foundational installation errors. First, interior wall topography. Amateur installations often utilize flexible, corrugated drainage pipes because they are easy to manipulate in a trench. However, the internal ridges of corrugated pipe trap moisture, dust, and organic matter, creating an environment ripe for mold growth. Sustainable systems require smooth-wall rigid pipe, such as Schedule 40 PVC or high-density polyethylene, ensuring that air and condensation move completely unimpeded. Second, condensation and drainage geometry. When warm, humid air makes contact with a pipe wall cooled by the earth to 54 degrees. Moisture immediately condenses out of the airflow. Over a standard summer season, an earth tube can generate multiple gallons of liquid condensation. To manage this, the entire run must be pitched at a minimum grade of 1/4 inch per foot, sloping downward away from the living structure toward a dedicated drainage terminus or gravel-filled dry well. This guarantees that condensation drains safely into the deep soil matrix rather than pooling inside the airway. Third, intake orientation and microclimates. The intake riser must be placed deliberately. If the opening is positioned in stagnant, heavily vegetated, or high humidity zones, it will pull in saturated air filled with organic debris. The entry point should be elevated at least 18 to 24 inches above the ground level, capped with a 1/4 inch galvanized steel mesh to exclude pests, and located on the shaded, northern exposure of a property to ensure the incoming air is as cool as possible before entering the loop. The utility of an underground thermal loop shifts seamlessly when the seasons change. The same subterranean matrix that acts as a heat sink in July transforms into a heat source in January. When winter temperatures drop below freezing, for example to 12 degrees, the deep soil matrix remains anchored at its stable baseline near 54 degrees. As sub-zero air is drawn into the loop, it absorbs the stored thermal energy of the Earth. By the time it traverses the underground run, it exits into the structure at a temperature well above freezing, typically between 38 and 42 degrees Fahrenheit. While 40-degree air cannot heat a living room directly, introducing it into a home represents a massive efficiency gain. Rather than forcing a wood stove or a heating system to warm outside air up from zero, the system baseline is elevated by 40 degrees completely free of charge. Ventilation air no longer shocks the indoor environment, drastically reducing the overall fuel and energy load required to maintain comfort. The sweet spot for a residential thermal loop balances excavation costs against thermodynamic laws. Long-term studies show that efficiency gains plateau right around 100 feet of continuous run at a depth of 8 feet. Excavating a trench of this scale by hand is rarely practical, but a compact mechanical excavator can complete the task in a single afternoon. The total investment in raw infrastructure is comparable to a single month of peak summer utility costs. Once buried, the polymer walls of the airway are protected from ultraviolet degradation and atmospheric weathering, establishing a functional service life that easily spans a century. The reliance on complex, fragile grid infrastructure for daily comfort remains a modern convention, a design path normalized by industries that profit from continuous consumer participation. The alternative does not require a sacrifice of modern comfort. It simply requires an understanding of basic thermodynamics, a length of smoothbore pipe, and the willingness to look beneath the surface of the land.